Enterprise software architecture is undergoing a structural transition. We are moving away from passive large language models that simply generate text towards autonomous agentic systems designed to perceive environments, formulate multi-step plans, and directly execute workflows across third-party APIs and corporate databases. The prevailing deployment strategy relies on a simple assumption: deeper computation equals better performance. Engineers attempt to increase accuracy by giving these agents large computational budgets to run extended, step-by-step logical traces before taking action. This infographic of system performance metrics reveals the financial penalty of that assumption. Because autonomous agents operate in continuous memory, planning, and action cycles, they draw massive amounts of processing power. Unguided agentic loops consume up to 136 times more compute and energy per query compared to standard text generation. Look at the graph on the left side of the dashboard detailing accuracy correlation. The assumption that infinite compute yields infinite accuracy is empirically false. Beyond a specific threshold, marginal utility diminishes, and the trend line drops. The agent's logic degrades into unresolvable internal loops, a systemic vulnerability known as the overthinking paradox. During these extended logical traces, models begin to exhibit distinct behavioral symptoms. They generate rapid answer oscillation, constantly altering their intermediate conclusions alongside an unstable consonance trajectory. They also emit stylistic hesitation markers in their processing logs, outputting phrases like "wait," "actually," and "let me reconsider." Treating inference time compute as an unconstrained resource creates massive financial exposure. Endless internal deliberation drains API budgets without delivering any measurable progress on task resolution. This diagram introduces a metric researchers use to track cognitive degradation called the flip ratio. It measures the frequency of an agent shifting from a correct intermediate state to an incorrect final state, a negative flip, versus correcting an initially flawed path. At extreme computational budgets, that flip ratio surpasses 1. Further analytical processing actively corrupts a correct answer rather than fixing an incorrect one. Forensic telemetry shows a negative 0.54 correlation between unguided thinking trace length and final accuracy. In interactive environments, this overthinking triggers the deliberation action dilemma. The agent must balance understanding its environment with executing physical steps, but deliberative models consistently oversimulate, favoring prolonged internal thought over interacting with necessary external tools. This inward focus reliably induces analysis paralysis. The agent continuously processes historical states and generates redundant, homogeneous solutions, churning through tokens without ever executing a single API call to advance the workflow. The bar chart tracking the reliability decay curve demonstrates what happens when an overthinking agent eventually attempts to execute a sequential pipeline. The success probability does not hold steady. It plummets with every subsequent step. In multi-hop tasks, errors do not average out. They compound exponentially. Even an agent operating with a highly accurate 90% success rate per individual step will decay to a 35% end-to-end success rate over a 10-step workflow. The compounding decay of these unguided models drives a 58.7% task failure rate in live production environments. Relying on unguided multi-step agentic reasoning is a mathematical failure. Open-ended conversational orchestration creates unpredictable liabilities and must be replaced by strictly bounded, deterministic execution. The root cause of overthinking begins at the human-machine interface, driven by a phenomenon called epistemic miscalibration. Human operators naturally communicate using compressed, high-level business concepts. AI agents, however, rely on strict syntactic messaging and rigid database encodings. This creates a semantic translation gap, where the AI is forced to guess definitions because the metadata doesn't explicitly match the human intent. When an agent encounters ambiguous organizational jargon, like a column labeled "is active," or the broad concept of customers, it attempts to resolve the ambiguity internally. This triggers massive, token-heavy React loops, draining budgets before the execution phase even begins. This schematic details the Genesis 2.0 architecture, beginning with Rosetta Core. This module functions as a definitive semantic translation layer. The zero-trust semantic firewall actively intercepts ambiguous business instructions and maps them directly into predefined schema IDs required by the AI ecosystem. Instead of requiring humans to learn complex prompt engineering, Rosetta initiates an alignment loop. It actively interviews the operator to isolate missing variables and lock down strict boundary conditions before downstream processing is permitted. By guaranteeing 100% intent alignment upfront, zero compute tokens are wasted attempting to execute misunderstood instructions. The initial trigger for overthinking is neutralized. Once intent is perfectly aligned, the architecture treats computational tokens as a strictly rationed corporate resource. Phase 2 introduces Vanguard v3, a dynamic tiering module eliminating structural token overhead. Vanguard bypasses massive frontier models for simple requests, routing basic tasks to low compute pipelines. This precision routing slashes operational costs by 80% while maintaining speed. This graph tracks a metric known as the deep thinking ratio, which evaluates active compute efficiency. It compares the tokens that represent active logical work against tokens that serve as redundant filler. By monitoring this ratio across network layers, the system identifies the exact moment a token prediction stabilizes early in the sequence. Any subsequent depthwise processing is flagged as unproductive hesitation. When the deep thinking ratio drops, the system mathematically terminates the loop. This intercepts the negative flip ratio, preserving the accuracy of early assumptions while fully protecting the compute budget. But what happens when an agent bypasses early routing controls and still degrades into a deep, unproductive logical spiral? The system continuously monitors the agent's internal state using cognitive entropy limits, tracking the degradation of reasoning paths to identify unresolvable logical loops. When those entropy limits are breached, the system triggers the Aegis 7.2 kill switch, referred to as the God kernel. Aegis instantly executes a strict lock. It immediately freezes the cognitive operation in its tracks, halting any further token consumption, and prepares to vaporize the stalled process. Once the loop is frozen, the human escalation protocol takes over. The system alerts oversight teams, allowing human operators to intervene, assess the stalled reasoning trace, and reset parameters before automated API calls drain the corporate compute budget. Deploying autonomy without a hard boundary is an operational liability. The Aegis protocol ensures that exponential cost spirals and logic degradation are abruptly and violently contained. Managing internal cognitive loops addresses only the logic. In agentic systems, hallucinations manifest as fabricated API calls or false permission requests, errors that translate directly into physical corporate damage. Standard self-correction loops fail to mitigate this risk. When a model prompts itself to review its own work, it operates with the same logical blind spots, resulting in a random walk over the answer space that degrades correct initial configurations. This architectural node details the Adversarial Zero Hallucination Orchestrator, or AZO, which replaces ungrounded self-correction with a cybernetic closed-loop control system. AZO acts as an internal red team utilizing empirical falsification. Before external action is executed, it intercepts the agent's logic for cryptographic authorization. If the proposed action fails these semantic limits, it enters a zero-bias quarantine, and the rogue execution is immediately vaporized. Those vaporized errors are routed to the M4 ARC memory core and logged as permanent correction axioms. The entire enterprise network instantly learns from the failure, developing permanent systemic immunity to that specific workflow error. In this sovereign-grade architecture, truth is not probabilistically generated by a model guessing the next word. Truth is the sterile, residual data that survives multi-layered empirical destruction. To survive the friction of production environments, architecture must transition away from open-ended agentic frameworks and move toward programmatically enforced directed acyclic graphs, where every transition is governed by strict validation layers. This table reveals the outcome of deterministic boundaries. High deliberation alone yields a 29.1% resolution rate at an inefficient cost metric of 2.08. By applying an external overthinking filter instead, task resolution rises to 30.3%, while significantly reducing computational costs. By enforcing upfront semantic alignment, dynamically routing tasks based on complexity, and deploying adversarial kill switches, the exponential risks of autonomy are neutralized. In the modern enterprise, unconstrained AI is a multi-million-dollar liability. True sovereign-grade autonomy is only achieved through absolute deterministic constraint.